Don't tell me salt water. Okay. Part 3, short answers. It says define the phrase solubility of a substance. This is again where you need those 3 parts. It's the amount of a substance that can be dissolved in a specific amount of solvent. There's part 2, and it's at a specific temperature. So we've got part 1, part 2, and part 3. All right, number 2. Which 3 factors increase the rate at which a solute dissolves? Stirring. You could stir it, get it to go faster. You could increase the surface area, or you could change the temp. These first 2 things, it's not going to affect how much you can get dissolved. It's just going to affect how fast. So if you can only get 30 grams dissolved, it doesn't matter how long you stir for. It doesn't matter how small you make those particles. You're still only going to get 30 grams of the stuff to dissolve. But if you stir it and you chop it up in smaller pieces, you might get those 30 grams to dissolve faster, but you still can't get any more than 30 dissolved. However, changing temp, if you increase the temperature, not only will it dissolve faster, but you'll also be able to get more dissolved. That's assuming it's a solid. If you change the temp, if you increase the temperature, you can get more solids. The gases are the opposite. If you decrease the temperature, if you make it colder, think about a cold soda, you can get more gas dissolved there. Then it says how do those 3 factors affect the rate at which a solution dissolves. So you're explaining how that works. And I wrote the more water molecules collide with the solute particles, the more collisions that take place, the faster the solute will dissolve. So what can we do to get more water molecules colliding? Well, we can stir. Stirring is going to increase the number of particles colliding. We could increase the surface area by chopping it up into smaller pieces. That's going to increase the amount of space on which the collisions will occur. Remember, if I have a big chunk here, the particles that are deep inside this cube, they're not going to make collisions with the water. But if I cut this, and I open it up, then those particles on the inside are now exposed to water. They're going to be able to make collisions. And then if I cut another little chunk, particles stuck there are going to be able to make collisions, and so forth. So we want to just keep breaking this up into smaller and smaller pieces so there's more and more surface making collisions with the solvent. And finally, if we increase the temperature, we can increase the motion of the particles. They're moving around faster, and then obviously they're going to make more collisions. Number 4, I've mentioned this quite a few times. It talks about how are the solubilities of gases affected by temperature and pressure. Just think about a flat soda. More gas can be dissolved in a solution when it's colder and when the pressure is greater. As soon as you warm it up, it's going to go flat. You're going to have less gas. As soon as you pop the top on a soda or open it up, you're going to have molecules of carbon dioxide coming out of solution. So the more pressure you have, the longer you keep that sealed, the better off you're going to be, and the less your soda will go flat. Now, number 5, we got some math here. It says, what's the molarity? I'm not going to give you the equations. You need to know, but it's simple, because molarity is going to be moles, hence molarity, over liters. And we're going to divide through, so we always end up with 1 liter on the bottom. So we're ultimately trying to find out how many moles would there be in 1 liter of solution. Now, normally, we don't always work with exactly 1 liter. In this case, we've got 0.65 liters. And we know that in the 0.65 liters, there's 1.22 moles. And then you divide the 2, and you should get a final answer of 1.877, you could say. Actually, we'll go with 2 sig figs, 1.9. And then that's a big capital M, so that's 1.9 molar solution. Number 6, again, what's the molarity? So it's molarity equals moles over liters. Now notice it's moles, not grams. But yet you don't have moles. You're given grams in the problem. So you have to first do this behind the scenes conversion. You start with 510 grams times, grams goes on the bottom. You're trying to convert to moles. What number always goes with the word mole? 1. And how many grams is 1 mole of glucose? Well, if you knew the formula, you could add up all your carbons and hydrogens and oxygens, or you could just look right here. I helped you out, and I gave you the formula. So it's 180.0 grams. Multiply across the top, divide through by the bottom, grams cancels out, and you end up with 2.8 moles. Now that's, like I said, just behind the scenes. That's just taking your mass of glucose and converting it to moles. Now we actually have to run the problem. Molarity equals 2.8 moles over our volume. And our volume is 350 milliliters. Now it needs to be over liters, so you're going to divide through or move your decimal point over 3 places right there, and it's 0.350. Divide the two, and you end up with an 8 molar solution. 8 molar solution. All right, solubility chart here. We've got a basic chart. You look on the side. This is standard. How many grams of solute you can dissolve in 100 grams of water. So this is all based off of 100. Now it says how many grams of NaNO3 can be dissolved in 100 grams of water at 18 degrees Celsius. So go find 18 degrees, which is right around here. Then go to the NaNO3 curve. So go all the way up till right about here. And see where it crisscrosses the line. That's how much you can get dissolved. So maybe 86-ish. Again, as long as you're in the ballpark, you're okay. I should see no more than maybe a 3-gram difference between your answer and my answer. All right, what's the solubility of NaCl in 100 grams at 90 degrees Celsius? So find 90 degrees Celsius right here. And then go up to NaCl, and it crisscrosses right there. So we'll say just about 40, maybe slightly under 40 grams. Okay, that's how much we can dissolve in 100 grams of water if the temperature is 90 degrees. Which one's most soluble at 80 degrees? KNO3, NH4Cl, or NaO3? So we're looking at 80 degrees, so go find 80, and then go find those three points on the lines. So we've got KNO3, which is going to be way up here, even higher. And you can imagine that this is just going to keep going up, 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 up. So that would probably be way up at that point at 80 degrees. NaNO3 is another one at 80 degrees. And our final substance we had to look at was KNO3, or was NaNO3. Nope, I did that one. NH4Cl, this one. So our final substance is NH4Cl. We look at those 3 points. Which one's higher? The KNO3. I'm not going to write it, I'll just circle. KNO3 should be your final answer right there. If it wasn't at 80 degrees, if it was at a lower temperature, you might get a different situation. For instance, if it was at 20 degrees, and you look at those 3 curves again, we've got NH4Cl would be right here. We've got the KNO3 would be down here, and we've got NaNO3 would be up here. So if it was at a different temperature, we'd end up with a different answer. NaNO3 would be most soluble at this temp, but things change when you warm it up. All right, letter D. Imagine 50 grams KCl are poured into 100 grams of water at 10 degrees. What mass of KCl will not dissolve and remain on the bottom? So we're looking for KCl, so we'll find our curve KCl right here, and we're dealing with 10 degrees, so find your temperature. There's your temp. And it says we put in 50, so there's a point right there. 50 grams are added in. But yeah, according to the curve, here's KCl, we can only get in right there. So that's a difference of 10, 20. So 20 grams is going to sit at the bottom because we're 20 grams above the line. Then it says, to what temperature must you heat the solution to dissolve it all, the one in D. So we've got 50 grams right here. We've got 50 grams. We want to heat it up until it all dissolves. So we go this way until we hit KCl right there. So we have to heat it to about 80 degrees, and then it'll all dissolve. All right. Next 2 questions. It says, imagine 40 grams of KNO3 are poured in 200 grams of water. That's important. We now know that the question's saying we've got 40 grams in 200. The only catch is, and this isn't going to be difficult, but we need to think. The only catch is that this graph is based off of 100 grams, not 200 grams. So we're basically going to say, how much would this be if it was only 100 grams of water? 40, 200, x 100, x is going to be 20. Half of 40 and half of 200. So 20 grams. So now we can kind of reread the question. It says, imagine 20 grams of KNO3 are poured into 100 grams of water at 20 degrees. What type of solution is produced? So let's find 20 degrees. Let's find KNO3 and 20 grams. And actually, let's get rid of some of this stuff on the photograph. It's getting a little crowded up there.